Now that we finished the first step, let's now move on to the second step, which deals with adiabatic expansion, where the temperature is now going to go from TH to TC. So by definition, since this step is adiabatic, we know that the heat for this step is equal to 0. And then also we saw that for adiabatic reversible expansions and compressions, the change in entropy is also going to be 0 as well. This is something we previously talked about in chapter 4. So those two things are just going to be equal to 0. Now for the work, back in chapter 3, we previously derived that for an adiabatic sort of expansion or compression in a piston cylinder device, your work would be equal to this. So T final minus the T initial, where gamma is equal to Cp over Cv. And in our case, since we know what the Cp and Cp values are, if we actually calculate that ratio, we get about 1.4. Okay? Now, this equation, if you don't remember where it came from, please review chapter 3, ICP 3 for the derivation, where in that problem we looked at the expansion and compression of a piston cylinder in adiabatic conditions. Okay? In any case, to calculate work for the adiabatic step, it's fairly simple, right? Because we know all these things. So here it is, just plug and chug. So W2 is equal to 4.16 e to the 3 joules. Alright, so we have those values, so we could go back to our table and we could fill in. We looked at expansion. Now in step 3, we're going to look at compression. So we'll start off with an isothermal compression step. But this time it's going to be at T is equal to Tc. Alright? Now, really the equations, to get the equations, we would basically do the same thing we did in step 1. Right? So we would just show that the heat is equal to the negative of the work. And for the entropy, change in entropy, it would be the same sort of equation. But really the only difference now is instead of operating at TH, we're going to be operating at TC. Okay? So that's what our work equation is going to end up being. And as such, this is the value. The heat is just going to be the negative of that. And delta S, which basically has the same functional form that we saw back in step 1, is going to be this, 4.4 joules per Kelvin. So we'll fill in. 2.53 e to the 3, negative 2.53 e to the 3, negative 4.4. Okay, and the last step, the adiabatic compression, is basically the same calculations as step 2. Except now the temperatures are reversed. So Q4, adiabatic, so that's equal to 0. Delta S4, adiabatic reversible, that's also equal to 0. And then the work. Let me erase that. It's going to be still R over gamma minus 1. This time it's TH minus TC. But it's just positive 4.16 e to the 3 joules. Okay? Alright, so we calculated the work and the heats and the entropies for all of our steps. So what I'm going to do now is, because to calculate efficiency, we want to calculate the sum, the net work, and the net heat, and things like that. Okay? Alright, so what we're going to do is we're going to add up all the values in the work column, all the values in the Q column, and all the values in the delta S column here. Okay? Alright, so in the work column, if you'll notice here, in the adiabatic steps, the work magnitudes are equal, the signs are just opposite. So those terms actually cancel out. Okay? And so all we're going to be looking at really is the sum of the isothermal steps. Okay? And if we add those together, we're going to get negative 880 joules. Similarly, for the heat column, I mean, these are zeros, so you don't even need to worry about them. But when you add these up, what we're going to get is positive 880 joules. And interestingly, if you add up all the entropy values, everything cancels out. So you're just going to get 0. And that's a good check, right? Because with the Carnot cycle, it's supposed to be completely reversible, right? And so that means that after we complete one cycle, there should be no change in entropy, right? And that's confirmed even if we go through each of the steps, right? Okay, in any case, so this value right here, this is going to be our W total. And so when we calculate efficiency, now it's going to be equal to the negative of W total over our QH, right? Which is the Q from the first step. So when you divide, you don't divide by the total Q. No, you divide by just the Q that's needed from the hot reservoir. Okay? Alright. So here we're going to do negative of negative 800 joules divided by 3.41 e to the 3 joules. If we take that ratio, we get a value of 0.26 or 26%. Okay? Okay, so that's the efficiency, you know, we calculated if we went through all of the different steps of the Carnot cycle. But in general, if you only cared about just the pure efficiency of the Carnot cycle, you actually don't really need to go through all those steps, because previously we just showed that for a Carnot engine, the efficiency can just be calculated based on knowledge of only the temperatures. Okay? In fact, if we just use the Carnot equation that we derived previously back in chapter 4, you get the same exact number as you do if you go through each of the steps in detail. Okay? So that's a good sort of sanity check. You know, if you're ever doing one of these Carnot cycle analyses, you know, in the end, when you calculate the efficiency this way, it needs to be equal to the efficiency calculated by this equation, just based on the definition.